Okay, thanks, Chair, for the introduction. I'm Mei Yuanxia from Shanghai Jiaotong University. Today, my topic is Slim, which aims to provide easy abstraction for the mobile developer to leverage cloud resources. This is a joint work with Jinghao Shi and our advisors from Microsoft Research Asia, Mingwu, Lingtao Zhang, and Cici. First, let's take a look at the motivation. We observe that mobile plus cloud applications are becoming more popular than ever before, and the cloud can produce the data, process it, as well as our some display problem. Okay, let's continue. Cloud can produce data, collect data, and process data. And it is important to get some additional points for the application to leverage the resource of cloud. Currently, there is virtual machine granularity and a procedure core level partition. Also, there is some work to expose explicit event to user to handle. And Slim takes a different perspective. We want to partition the application from the data structure perspective. Because we believe that over time, data structure continue to be the core part to derive program logic. Okay, let's move on to the goal. First, we want to preserve familiar interfaces. So we view Slim as a common library of data structure, and currently we expose STL-like interfaces. Then, since Slim targets mobile plus cloud storage system, we need to adapt to the new memory hierarchy where there is main memory, flash, and the cloud. Third, since cloud should not be treated as a giant storage backbone, we also want to shift the part of the computation to the cloud. So here is a set of applications we have modeled with Slim data structures, among which 3 have been implemented with current Slim prototype. And we also developed a Slim policy to allow users to have a fine-grained control over data structure behaviors. The level policy shows where the data can be stored. Direction policy shows how data move. For example, we have provided single direction policies for consumer-producer model. Also, bidirectional cases are possible in real world, such as a mail client. The user can delete old mails, while the cloud can push new mails to user. And the consistency policies shows how the data updates are dispatched. Policies help users to alter the behaviors as well as gain some performance improvements. Let's give an example to show this. We use the instant message, which can be modeled as a pair of message queues. Alice defines a Slim queue with device to cloud policy to map her message from the device all the way to the cloud. And then Bob binds to the same queue with different direction policy to map the Alice's message back from the cloud. Likewise, Bob can define another outcome queue to send messages to Alice. Undoubted round 1 here better illustrates the instance notion, where data are synchronized once they are produced. Here's another example showing how to vary policy selection to implement different application functionality. In this scenario, the sensor nodes maps a shared Slim data structure from the collector application in the cloud. With different consistency policy, the sensor can implement either periodical reporting or the batch update. Now we have Slim data structures and policies. Next, I want to show you how to compose a Slim application with them. We use ISS case as an example. Traditionally, device pulls data, XML data directly from the source and pass it and find out a new one to display. With Slim, we insert the cloud in the middle, and code is then split into two parts running in the cloud and device respectively. Shared Slim data structure serves as the bridge for them. In the device part, it defines a shared Slim vector to receive new feeds from the cloud. Cloud takes care of the XML batch and parsing. Then, whenever there is a new ISS feed from the source, cloud will notify the device. Device only need to bind a callback function to handle the new ones. By deploying in Slim, we have transformed the stateless spectrum to event-driven update. And currently, our code is partitioned manually, but in the future, we want to investigate automatical partition. Then in this case, let's see how we benefit from Slim partition. Traditionally, ISS reader fetch a window of feeds to search for the new one. But in Slim case, we only transmit the latest feeds. This leads to obvious network traffic saving between the device and the cloud. And here is the results. We test under different fetch window the network traffic saving ratio we can gain. 4 bars demonstrate different feed size. As shown, since we cut the redundant feeds to be transmitted between the cloud and the device, we observe obvious benefits of traffic saving. Okay, here I want to show another example to show application can compose more complicated functionality. We use inverted index building as an example. This task is very useful for applications such as mail clients, which can accelerate the search for certain keywords. Following the last example, we want to build inverted index upon the ISS feeds array. First, we define an index vector type. Then we map the inverted index from the cloud by declaring a shared Slim map. The cloud will start fetching and build the index ready. Finally, device can use the common get interface to query about the keywords. We've seen Slim data structure policies and how they are employed to compose the application. Now let's take a look at the design for the prototype. We start from the L2 cases where there are only memory and flash. In data structures, pointers are commonly used. The problem is that the data being referenced may not always reside in the memory. So we developed the polypointer mechanism to assign universal address to data managed by Slim. Polypointer exports traditional pointer semantics such as the dereference and the self-incremental to user, while hide where the data actually is. We use the pointer swizzling technique to approach native performance. The pointer swizzling technique is sort of complex.